Now that we've gone over the methods that need to be written for the DynArray class, let's do some diagramming for a handful of these larger methods to better visualize what's going on in each of them. We'll start out with the default constructor. As we talked about in the slides, the constructor is going to take in a starting capacity as an optional data member. This will inform us of whether we need to allocate our array to a value or if we should leave it at null. So let's go ahead and write down our data members over here. So we have our array, which is a pointer, right? A dynamic array of some type, whatever our template argument is. We have a capacity, which again represents the number of elements in the array, and then we have the size because the array may not be full. So our capacity and our size are not always going to be the same value. So if they pass in a 0, then we want to set all of our data members to point to 0, right? We have no array. We're not allocating any memory yet, so that should be null. If we don't set that to null, C++ will just leave it at some random address, something that we would consider undefined or garbage. And we would also have a capacity of 0 and a size of 0, right? Now, if they don't, or if they do pass in a value rather, so let's say that they pass in a starting capacity of 10, then we would set our capacity to 10. We have the ability or the space to store 10 elements worth of data. And we would allocate our array to point to some dynamic memory out on the heap that is 10 elements. I believe that's 10. One too many, so we'll get rid of that. So that would be the constructor. So if they pass in a value, then we need to allocate our array to be of that size, and we also want to set our capacity to that. The size should still be 0. We've got an array here that we can store 10 elements worth of information in, but we're not actually filling that array with anything yet. That will be handled inside of the append method. The next method that we'll attack here is the append method. This is where we're going to actually be storing new values into our array. And that takes in a type reference, or more specifically, a constant type reference to whatever we want to store, right? We'll call it, in this example, we'll call it the data. Now, in this diagram here, we've already called the constructor. We've told it that we want to have a starting capacity of 2. So we have our array pointing at our dynamic memory that we've allocated, and we have our starting capacity of 2, but we're not storing anything yet. So we have 2 empty elements here. So all we would do within this method is, if we have room, we want to store it in the next available index. So, of course, we know that arrays start at 0, so we have index 0 and index 1 here. So we would store the data inside of index 0 because that's the first empty one. So we'll say that we have a value of 5. Let's just say we're storing integers. And so then we would increase our size to 1 because now we're storing 1 piece of data. Then we call this method again. We can see that we have room because our size is less than our capacity, so we could store another value, 2. And again, the size would then increase to 2. Now, if we want to append a third piece of data, we're not going to have room for it, right? Because our size is equal to our capacity. The array is full. So what we would do in that case is we would ask to reserve more memory by calling the reserve method. And that's what we'll talk about next. Now that the array is full, we need to reserve more memory before we can append again. So, as we talked about in the previous example, if we call append and there's no space to put that new piece of data, then we should go ahead and reserve more memory at that point so that we have the space to store this. So let's take a look at reserve, which again, like the constructor, has an optional parameter. So it takes in a new capacity. I'll just say new cap, and that's going to default to 0. As we talked about in the slides, this has 3 different cases that we can fall into. I'm not talking about a switch case here, but there's 3 different scenarios that can happen. If they pass in a 0, right? So if the new cap is 0 and the capacity is 0, so if the new cap is 0 and our capacity is 0, then we will set our capacity to 1. And that's for the next step of if the capacity is 0 and the new cap is not 0, right, then we are going to double our cap. Okay, so obviously that wouldn't work if the original capacity was 0, because doubling 0 is still 0, right? So the first time we come in, if we haven't allocated anything yet, then we're going to go ahead and allocate an array of 1. And we'll do that allocation here in a little bit. And our capacity would need to be set to 1, right? Otherwise, we would double, right? And then the third scenario that could happen is they passed in a new cap. So in that case, we would set our capacity to the new capacity as long as that new capacity is greater than our current capacity, right? If it was smaller than our current capacity, then we would end up potentially losing some data out of our DynArray, which is something that we don't want to do. Okay, so once we've figured out which case we fall into and we've gone ahead and updated our capacity, we then need to make more space, right? We know from systems programming and from the earlier slides that an array is of a fixed size. So we cannot add additional elements into this array. We're going to have to make some more space. So that's what we're going to do. We're going to go ahead and create a new array. We can call it whatever we want. I'll call it temp. And we're going to allocate that dynamically to point to some memory, a new array that is of the appropriate size, whatever our new capacity is. So in our case, let's say for this example, I didn't pass in anything into new cap, so we just used the default of 0. I already have a capacity of 2, So that means that temp would be an array of size 4 because we would double our current capacity, right? So now what I need to do, after I've allocated that array, I've now called new twice, and I'm going to copy over the data from my data member array, right? Because this temp, that's going to be where I'm going to be adding things to in the future. And so I need to copy over all of the existing information. At that point, right, well, let's, I forgot to update my capacity, right? So my new capacity was size 4. Now, I don't need this anymore, right? So we can delete this, right? So now we've cleaned up that memory in the constructor or in reserve in a previous call. We called new for this array, right? So we need to delete that. And then I want to reset that pointer to point to this new memory that we have allocated. So now my data member points to that new memory. I have a pointer to it. I can delete it in the future if I need to, in the destructor, in my assignment operator, in reserve again later on, right? And then at the end of the function, this pointer here, temp, that's local, so that's going to go away. And that's the key to this class and how we can make it appear that we have an array that can just keep resizing itself and growing larger, because it's not actually a single array. We keep allocating memory and pointing to that new memory, right? So we always have just one array, or I guess we have 2 arrays temporarily within this method, but we only have one array that we're working with. It's just a different array. It's somewhere else in memory as we move along, but it keeps becoming a much larger and larger array. Lastly, let's take a look at the rule of 3, specifically the assignment operator. This is the one that you'll actually probably write, as we can use a trick for the copy constructor to actually call the assignment operator. So let's go ahead and look at a couple of situations here. First off, we'll look at the most common situation where I am assigning one object over the top of another object. So let's create and diagram out a couple of objects here. We'll use object 1, and we'll say that he has his array pointing to some array, and it has, maybe it has some values in it. So that would have a capacity of 4 and a size of 3. And then let's create another object, object 2, and we'll say that this one has an array of size, let's say 5 or 6, I guess I can count, and it has some values in it. So we'll say that it has the values 2, 3, 4, 7, 2, and so that would have a capacity of 6 and a size of 5. And so let's say over in main or somewhere outside of this class, we are going to set object 2 equal to object 1. Okay, so that means that I need to make object 2 a duplicate of object 1. Now we have to remember that we called new to allocate these 2 arrays, right? So I need to clean up that memory first, right? The one thing we don't want to do when dealing with dynamic data members is do a shallow copy, right? Where we would say something like my array is equal to their array, whatever we called this object in the parameter. We'll say it's just called DA, right? DA dot array. Because what that would do is it would take my pointer away from this array that I've allocated and point it to the same address that we're pointing to in the other class, right? So now I have a memory leak, for one, because I have lost the address to this array, and I now have two objects pointing to the same memory. When one of them eventually deletes that via reserve or clear or the destructor, the other object is still going to be pointing to that address, and therefore we're going to experience a crash. So we do not want to do this. So let's back up and get rid of this. Okay, we need to do a deep copy. Obviously, we're not going to write the code here, but we're going to diagram out what needs to happen. So the first thing that I want to do is I want to delete this array. Right? I need to clean up that memory. That is no longer needed. Now I can reallocate array to point to some dynamic memory of the appropriate size. We know that the appropriate size is 4, so we'll go ahead and dynamically allocate our array to be of size 4. Right? Now we can go ahead and copy over the information. So one element at a time, I need to copy over the data into the new array. Right? We also need to shallow copy any non-dynamic data. So our capacity is no longer 6 and our size is no longer 5. Our new capacity is 4 and our size is 3. Right? Now this step here, where I'm assigning the shallow copies, right, the non-dynamic data members, that can be done before or after that deep copy section. Really depends on the order of your logic. It may differ depending on what you need to do from class to class. In this particular class, the DynArray, the order really doesn't matter too much. So now that we've copied over our data, now we're done, right? And object 2 and object 1 are storing the same information. Now, lastly, let's look at what would happen if we tried to say object 1 equals object 1, right? And this would be a self-assignment. Now, we might say, well, like, why would we'd never write this line of code? And that's probably true, but we may do a self-assignment via some algorithm that happens, or we may be dealing with a pointer or reference to where it doesn't look like a self-assignment, but it is. Okay, so we'll get rid of object 2 here. We don't need that anymore. So if I was to run through that same logic that we just talked about, then what would happen is we would delete our array. Right? That was like one of the first steps that we talked about. So I would delete that array. I could then reallocate a new array, right? But I would still be pointing, or I would dynamically allocate myself a new array. I wouldn't have anything to copy, right? So that would be a problem. And we could potentially experience a crash, or at best get some garbage data in there. So we always want to make sure when we're doing an assignment operator, the first thing we do before we get into any of the logic and copying is to do that self-assignment check and make sure that our two objects, the invoking object and the object being passed in, are not pointing to the same memory location, because that's what's going to determine if we're unique or not.